Okay, so who can remind me? Because we've got really kind of three camps. Can I talk about the three different? We'll do it regardless, even if I did it. This is a recap. So we've got complete dominance. Yep. Good. And who can remind me what's the difference of these three? Okay. Actually, you know what? Discuss that with your partners. Okay. Discuss the difference and an example of each of these three. Okay. All right, and who's got it? Who's got it? Oh yeah, let's hear it. Okay, so you're saying like, okay, that is homozygous dominant. Okay, I will say that it is in each example here. I just picked ours at a random, right? So that's homozygous dominant. Where does this really come into play, though? What genotype? Ooh. Which genotype does this really become important when whether which example we're talking about?
I don't know.
Yeah, so that one right there. So when we're talking the heterozygous one, okay, so the capital lowercase one, that's where this becomes really important. Let's say, for example, that the capital allele is red, okay, and the lowercase allele, so the lowercase r, is white. Then we're talking flowers, okay? In this case, the capital R, lowercase r would be what color of flower? Red, right? Yep, it would be red. It would be a complete dominance. It would be red, right? In this case, maybe this one's easier. What would the incomplete dominance example be? What would this be? Okay. It'd be pink. What about this one?
Is that in the mixer? It'd be red and white.
Yes, it's red and white. That might show up as stripes. I might show a picture because I think that's kind of cool. Okay. Yeah, so it could be stripes. It could be dots. Sometimes flowers have like a dotted pattern. Okay. Yes.
Or the like fadey thing flower petals have, where it's like the one color.
Ooh.
And then
Yeah, that'd be good as well. Like a fade or like a color gradient. That's good. Yep. I might find some pictures of some of these. Yeah, maybe I can find some codominance patterns of some flowers because I like images. So we'll see what we can find. Oh, here we go. So that's one of them. Okay, see how we've got white and red. This would be an example of incomplete dominance. That's an example of the striped pattern I was talking about. Let's see if we can find one of the gradient ones that Claire was talking about where it goes. Oh, this is a good example. These are really cool. Okay, again, codominance. Okay, codominance, both equally represented. Incomplete, that's a good example, just the pink flower. Okay. Okay. Is there any variation in this one? The double recessive one, what's that one always? What color is that one regardless of the example? That is white, right? Those are white flowers regardless, whatever you're talking about. Those are the white alleles. Good. Okay. What's a good example of codominance that we talk about in our bodies? What's an example that we talked about of codominance in our bodies? Blood type, right? Yep. So blood type is an example of a codominance. Okay. Blood type, we have 4 different types. What are they?
O, A, B, B.
Anyone agree with that? Agreed. Cool. Yep. Those are the 4 types. This one is like the recessive type, if there was. In a codominance, there really isn't a recessive because they both are dominant. Does that make sense? Okay. So they both show through equally, but this would be kind of like the recessive one. It's also the most common one, the O-type blood. Okay. You should have completed, and does anyone want to go through any of these examples? If you did, just kind of give me a slight hand raise on the codominance blood typing. Yeah, the one where you had the example a lot of folks liked. I guess I already have one of them done for us. Yeah, this one, like, who's the father example, okay? I think a lot of you found it was George, or was it the cable guy? George, yeah, okay.
I named him George Jr.
Yeah. So if you have not done this, okay, I would make sure to start with that one, but I don't think we have to spend a lot of time on it. I think we can switch to our next examples, okay? So you might want to take your notebooks out because I'm going to go through one main example of what we call dihybrid problems, okay? And one thing that I will say is up to this point, we've been talking about one trait. All 3 of these have been examples of one trait crosses, okay? One trait. And now we're going to look at what happens if we cross 2 traits at the same time, right? Because one thing that's common is most genes and traits aren't just one gene, right? It's like multiple. We call that like polygenetic traits. Most of your traits are what we call polygenetic, meaning they're a collection of, I think eye color is like 3 or 4 genes that actually express it depending on your eye color, okay? So like that would be a cross to actually determine eye color is a pretty complex Punnett square, okay? So we're going to go through an example of a dihybrid, and to do that, I've kind of got, it's a YouTube video. It's only like a minute long, but it's got the problem on it. I'll probably pause it at a couple points and talk about it, but we'll just introduce it, and then I think that'll be good. So you can kind of write it down in your notes as we go through it.
In werewolves, long fangs are dominant to short fangs, and red eyes are dominant to black eyes. If 2 heterozygous for both traits, werewolves mate, what % of the offspring are expected to have long fangs and black eyes? So this is called a dihybrid cross because you're looking at 2 traits at the same time. We're looking at fang length and we're looking at eye color. So first, let's assign our alleles. It says that long fangs are dominant, so I'm going to say big F is for long fangs. And then I'll say that little f is for short fangs. And then let's say, since red eyes are dominant, I'm going to say big E is for red eyes. And little e is for black eyes.
Okay, so we've got 2 alleles that we're looking at. Now we're looking at 2 traits. So the 2 important traits clearly with werewolves are their fang length and eye color. I don't know if they're actually important or not. I've never met a werewolf before. But long fangs, okay, that's capital F. That's the dominant trait. Short is the recessive, okay, and then eye colors. Red is going to be our dominant trait, which is kind of unique, and black is the recessive, okay.
There's several different ways to do dihybrid crosses. I think the easiest way is to actually use 2 Punnett squares. So you guys are familiar with doing 1 Punnett square at a time, but here we're going to use 2. So the problem says if 2 heterozygous werewolves mate, what percent of the offspring are expected to have long fangs and black eyes? So it says they're heterozygous for both traits. So that means both parents have this genotype. So what we're going to want to do is do a Punnett square for the F's and then do a Punnett square for the E's. So let's do our F's. Again, both parents are heterozygous. And then do one for the E's. So this is a part that you guys have done before.
This part's pretty standard, but one common mistake that happens a lot, and it will probably happen today too when you're doing practice problems, is a lot of folks try and to combine like first parent and one parent Punnett squares, like F's and E's, and then F's and E's. You put all the F's in one, right? It makes sense, right? One trait per Punnett square. Okay, so this first Punnett square gets one trait, the fang wing. Okay, so that's the one we're crossing first. We're taking a look at what our potential offspring are. Oh, look at that. We could get all of them. The highest probability is that it's the heterozygous one. Okay, it's got a high probability of having long fangs as well, because this would be a complete dominance problem. Most genetics problems, unless they tell you otherwise, are what we call complete dominance, which means that is what? Dominant, right? It's the same as this. So this is long fangs, this is long fangs. This isn't one of those incomplete dominance problems where it's like intermediate fangs. It's not a co-dominance problem where they have one long fang and one short fang, right? It's a normal, most genetics problems are what we call the top option, which would have been complete genetic, or complete genetics or complete dominance, okay? So those are our Punnett squares. They're pretty standard, and you can go through, and she's going to go through as well, the different percents. Okay, so like if we're talking like long, like individually, it's pretty easy to see that 1, 2, 3 are all long fangs. Okay. Yes. You're already onto it, right? See that right there? That's a good indicator of what we're probably going to do to our probabilities. It's going to be multiple. Okay, but we'll get there. Have you done these before? Or are these new?
These are new. I just kind of guess.
Yeah, I'll be honest. It's kind of recycling the same. I should say it's rebranding the old idea that we've done. Okay, so I will go through and analyze them, and then she will as well. And for virtual folks, I'll make sure you can really get the whole. I guess she'll write it all out. So even if you can't see my board, you'll be able to get it from the problem, if that makes sense. Okay. Trying to bridge the gap here. It's not the easiest, but it's not too bad. Okay, so red, you should see that as 3 out of 4, 75% as well. Black, 1 out of 4, which is 25%. Okay, let's keep rolling.
So if you look at this Punnett square here, it looks at 75% of the werewolf offspring would have long fangs, and 25% would have short fangs, because only 25% are homozygous recessive. And then 75% would have red eyes, and 25% would have black eyes. So the question asks, what percent of the offspring are expected to have long fangs and black eyes? So long fangs, that chance would be 75%. So there's a 75% chance, or 0.75, that the offspring would have long fangs. And then for black eyes, that is a 25% chance. So multiply that times 0.25. So if you multiply,
you can see here, you got to look specifically at the traits you're looking at. So we're looking for ones with long fangs, so that probability, and black eyes. Now you can choose if you're a fraction person. Okay, then you can just do the fractions, okay, of this and multiply those together. I should say long, so it's actually 3 out of 4 times as long and black, right? Yep. Okay. You could also do the 0.25 times it. So you would have a fraction of 3/16 if you're a fraction person, right? Because you multiply them across. 3 times 1 is 3. 4 times 4 is 16. Multiplying fractions isn't really too bad, I'll be honest with you. So that's really not too terrible. Okay. Or you can do the 0.75 times 0.25. Okay. What's that get you? Like 18 point. 0.1875, right? Which equals 18.75%. Here's the deal. If I ask for a percent, I probably will want you to turn that fraction into a percent. There's some advantages to doing the fraction, though. We'll have her go through the problem, and then I'll show you how to do a ratio of all the different phenotypes. Okay, but I'll show you that once we actually finish this. Okay, so after running the numbers, I'll go ahead and turn this off now, I'll stop sharing so you can look at my whiteboard, virtual folks. Because now one thing that your problems will ask you to do is they'll ask you to find a ratio of all the possible genotypes. Okay, so I'll show you how to, or phenotypes or genotypes, depending on which one you're talking about. So I'll show you phenotypes first, just so we can focus on the ratio part. So ratios are always comparing like the amount of something to the amount of something else. So we've got to actually look at all the possible phenotypes, right? So one possible phenotype is long fangs and red eyes, okay? Another one is long fangs and black eyes. Another one is short fangs and red eyes. And then short fangs and black eyes, okay? So those are our possibilities. With ratios, I do like to work with the fractions, okay? So with the ratios, I always start, so the long fangs, okay, is 3/4. Got that from our Punnett square. Or short, okay, is 1/4. And then I have to multiply that. And I'll kind of get out of the way for the folks who are over here too. Okay, so our red is 3/4. Our black is 1/4. Black eyes. Red eyes. Black eyes. Okay, so now we multiply them. That's 9/16. 3 times 1 is 3. 4 times 4 is 16. They're always going to be 16. 3 times 1 is 3. 16. And then 1 times 1, 1. Okay, 16. I'll leave that up there for a while now because I know I wrote it up there kind of quickly. Okay. So now it's pretty simple to go through and do a ratio. Okay, there's a 16 on the bottom of all these, right? So I don't really need to write the 16. I can just write the ratio of 9 to 3 to 3 to 1. Okay, that's my ratio. So that's this to this to this to this. Okay, 9, 3, 3, 1. Now, if 1 was a 0, I'd put a 0 in, right? That's just fine, okay? That might take a little bit of getting used to. That is what we would have. That would be a phenotype ratio. And I'll get out of the way here after I write everything down. So that would be a phenotype ratio, okay? Because I'm looking at the actual traits. As a reminder, phenotype, which starts with a PH, right? Phenotype, physical characteristic, they both start with PHs. So phenotype's the actual trait, okay? Genotype is the actual genes. So it's always a series of 2 per trait, okay? So like the genotype of long things could be capital F, okay? It could also be capital F, lowercase f. And virtual folks, I'll take a look. How's this coming through on the recording? Is it okay? Oh, it's not great because I guess the actual fraction part isn't, the actual thing isn't too bad. The number, I got those fractions from those Punnett squares right there, okay? So I'll show you the Punnett squares too. Here they are. That's not great, is it? Yeah, that's not too bad. Okay. Questions? How's it? How do you feel about it? Do you feel like if I gave you practice problems, you could at least give them a try? All right, let's do it. So, well, one last thing I have to point out real quick before I'll show it to the virtual folks and then I'll let them free. Is this right here. And then I think we're ready to crush these problems. They don't even stand a chance. So the last thing is, how do we determine the number of possible phenotypes and genotypes in a given dihybrid cross, okay? So how many possible combinations do we have, okay? And the trick is after you fill each of them out, okay, after you fill out each individual Punnett square, you will have to count the amount of, in this case, we'll start with phenotypes, right? So if we look at this Punnett square right here, after we filled it out, right, we combined the G's. It was capital G, lowercase g, lowercase g, and we crossed them, okay? How many possible phenotypes do we have? We have 1, which is solid gray fur, okay? And we've got another phenotype, which is lowercase g, which is striped fur. Okay, so there's 2 in this Punnett square. And then in this one, we have green eyes, which is the dominant. And then we have blue eyes, which is the recessive. So that one's 2. And you multiply them together. 2 times 2 is 4 total phenotypes, 4 possible combinations. The genotypes are a little bit different, not because the process is different, but because we're looking at, we have 2 different genotypes that we could get the same solid gray fur trait or phenotype, right? We have 1, 2, 3 different genotypes in this Punnett square and 3 different ones in this Punnett square, which is 9 total combinations, okay? You will do these problems as well, but I'll have that as reference. You can reference it on Canvas. Virtual folks, you will do this one. You can't actually edit the PDF, so you're just going to type your answers into a text box submission. Like you'll just submit a text box with 1, 2, 3, and 4 answered, okay? In-person folks, I've got hard copies that you'll work with. And then I also want you to complete this one, virtual folks. Sounds good? So if you don't have any questions, virtual folks, you can bounce out and go ahead and work on those. Otherwise, you can stick around and work on them as well, but that's kind of up to you, okay? Perfect.